Our next topic is the null space of a matrix. Let me start with the definition, then we'll do some work involving these things. So first off, let me start the definition. Let A be an M by N matrix. Remember, that's the notation for this here is the notation for M by N matrices. The null space of A is the set of all x in Rn such that Ax equals the zero vector. And notice we say that x is in R to the n because the matrix here has n columns, and in order to make that multiplication compatible, we need for x to have n rows. So whatever you're putting here has to match the number of columns in the matrix. Let's do a couple of examples. Let's determine the null space for A equals 1, 2, 5, 4, 1, 9. So for us to solve this, we need, what do we need? We have 3 columns in this matrix. So we got 3 columns in the matrix. So that means I need my x to be in R3 with Ax equals. Now the zero vector here matches the number of rows of the matrix. So that will be some sort of a 2 by 1 vector. Notice the way I used to think of it is this matrix is 2 by 3 and x is 3 by 1, so you're left with a 2 by 1. The middle things, in my mind at least, cancel out. So anyways, let's go ahead and do the computations. If I change my A and put it in the numbers in, I'll change x to x, well, the vector x to x, y, z, and that has to equal 0, 0. So let me augment it. I have 1, 2, 5, 4, 1, 9, then 0, 0. So let me go ahead and row reduce this thing until I get as close to row reduced echelon form as I can. So the first thing I'll do is I'll take -4 times the first row and add it to the second row. So the first row, of course, will stay the same. Whatever, any column, or any row operations that I'm doing are still going to leave the zeros at the end. All right, so -4 times 1 is -4, so that will cancel that out. -4 times 2 is -8. If I add it to the second row, I have -7. And then -4 times 5 is -20, plus 9 is -11. Now what I'll try to do next is, like I said, get this as close to row reduced echelon form as possible. So I'm going to use this leading number here to try to wipe out the number on top of it. If I luck out, maybe I can do the same for the other one. In order to avoid fractions, here's what I'm going to do. I'm going to multiply the first row by 7, and the second row I'm going to multiply by 2. So let me write this intermediate step. I'll have 2, 4, 10, 0, 0. And then I'll have 0, negative, wait, I made a mistake there. Multiplying the first row by 7. I'll have 7, 14, 35. And the second row, since I'm multiplying by 2, I'll have negative 14 and then negative 22. Now simply add row 2 to row 1. So the 7 will be unaffected. Now this negative 14 here will cancel the 1 above it. This negative 22 will leave 13. And then I'll have 0, negative 14, negative 22. Just so it's simplified as much as possible, I'm going to divide this second row by negative 2. So I'll do negative 1/2 times R2. So I have 7, 0, 13, and the zeros at the end. And then I'll have 0, 7, 11. So recall that this sets up the couple of equations. 7x plus 13z is equal to 0, and 7y plus 11z equals 0. So since z is involved in both of these equations, I can solve x and y in terms of z. So x will be negative 13 sevenths and z. I probably shouldn't write that way. I hate when my students do that. I don't know why I did it. So x will be negative 13 over 7z, and y will equal negative 11 over 7z. Z is a free variable. So if I wanted to describe the null space, I would describe it simply as this. So what we'll have is we'll have the set of all numbers. So I'll have negative 13 over 7z, negative 11 over 7z, and then z can be anything itself. And this would be such that z is in the real numbers. Notice that this is the same as the span of the following vector. I'll try to give myself a little more space this time. Negative 13 sevenths, negative 11 sevenths, 1. That 1, of course, right there is where the z was. So whatever z is, that will drive the whole vector. Anyways, it can be written as the span of this. So you can see that the null space, as they call it, a space, makes sense. It's actually a subspace of r to the third. Notice this, one other thing though. I just want you to see this. I could have written it as the span of the more enjoyable looking negative 13, or just 13, 11, negative 7. This way I can avoid fractions in my presentation here. So all you got to do is if z is equal to 7, it will wipe out the denominator. If z is equal to 7, it will also wipe out that denominator. And then the negative is just there so that the majority of the entries are not negative. So that takes care of a description of the null space for that particular matrix. Let me do another example. Let's compute the null space of, this time A is going to be a 3 by 4 matrix. I'll have 1, 3, 1, 262, negative 250, 143. Hopefully you can see right off the bat that column 1 and column 2 are, well, column 2 is a multiple of column 1, so these columns are not linearly independent. What that means is I'm going to most likely end up with free variables when all is said and done. So there's my vector A. Let's go ahead and see if we can compute the null space. So this time, if you look, we have 1, 2, 3, 4 columns. So anything I'm looking for to be a solution has to be has to have 4 rows in it, or the vector has to be a 4 by 1 vector. So what I'm going to do is I'm going to allow x to equal x, y, z, and then w. And that, of course, is in r to the 4. So we're going to let x be that, where ax is equal to the 0 vector. Of course, the 0 vector here is in R3. That matches the number of rows of the matrix. All right, so let's go ahead and do our computations. Just like before, I'm going to end up with an augmented matrix and work from there. There should be a negative 5 there. Okay, so I am going to multiply the first row by negative 3 and add it to the second row. And then I'm going to just take the negative of the first row and add it to the third row. So 1, 0, 0, 2. Negative 3 times 2 is negative 6, so I'll zero out of that entry. Then just negative 2 plus 2 will zero out that entry. And then negative 2 times negative 3, well, let me finish this row because it doesn't matter. It's not going to be used. It'll just hang while we do the rest of the computations. So negative 3 times negative 2 is 6, minus 5 gives us 1. And then negative 1 times negative 3 times 1 is negative 3 plus 4 gives us 1. And then negative of this number will be 2, and I add it to the third row. That'll put 2 here. And then negative 1 plus 3 will be 2 as well. I can wipe out the third row just by taking negative 2r2 plus r3. So I have 1, 2, negative 2, 1. These zeros, of course, will be unaffected by anything that we do. 0, 0, 1, 1, and then finally 0, 0, 0, 0. Now, once again, I'm going to try to go as far into row-reduced echelon form as I can. So in particular, I'm going to take twice this row, the second row, and add it to the first row to wipe out that particular item, or that entry. So I'll take 2r2 and add it to r1. So, well, the good thing about this is the first 2 entries are going to be unaffected. Now, twice 2 times 1 plus negative 2 will be a 0, as planned. And then here, 2 times 1 plus 1 will give us a 3 in that location. So as equations, this is what we have. Now, what I see here is y is only mentioned in one place, and we can solve the first equation for x and the second equation for z. There's more. I could solve the first equation for y if I want to, but leaving w on the right-hand side, leaving the w's on the right-hand side is a good idea because w is a free variable. Since I'm going to solve x in terms of y and w, then y will also be a free variable. So I'll have negative 2y minus 3w, and then z, of course, will equal negative w. So when I write my null space out, here's what it's going to look like. Remember, these are, where are they from? They come from R4. So I need 4 rows in my vector. 1, 2, 3, 4. All right, so I have enough. 1, 2, 3, 4. Well, the x look like this: negative 2y minus 3w. W could, or y could just be y. Z is equal to negative w, and then w can just be itself, such that y and w are real numbers. Now, recall that I can break this up into the following. Recall that I can rewrite that set as the span of the following vectors. If I consider vectors using only y's, I can have a negative 2, a 1, but then there's no y's in these last 2 rows, so I can do zeros for those. And then over here, assuming basically what you can do is let w be equal to 0 to get this vector. Now I can allow y to be 0 to get this vector. And each time you have a free variable, it's a good idea to allow the free variable to be 1 to give the simplest explanation of these vectors. So here the free variable was y, here the free variable was z. And not only have you found the null space, you happen to also see that it is a space because it's the span of 2 vectors. So automatically it's a subspace of R to the 4. So note that null A is a subspace of R to the 4. This video is pretty short because there's not a lot to say about the null space. We're going to be more interested in how it reacts or interacts with the column space and some other ideas. So let me end this section with a theorem. It says the null space of an M by N matrix is a subspace of R to the N. Remember, it's got to match, the number of rows has got to match the number of columns of the matrix. That's why it's a subspace of R to the N. And really, nowhere in this proof are we going to do that. But first, note this: for number 1, the 0 vector is in null A. Well, because A times the 0 vector is automatically the 0 vector. For part 2, if U and V are in null A, then A times U plus V, I'll use the distributive property that holds for matrix multiplication. Well, each of those things is the 0 vector, and when you add the 0 vector together, you still get 0. So this implies that U plus V is in null A. And finally, let C be a real number, and let U be in null A. Then, if I take A times CU, you can actually pull that C all the way out front. I want you to think about this for a second. Because you can multiply on the right or the left by a constant, it's not going to matter. All that constant does is multiply every single entry in A by that constant, by that C. Well, I can also then factor that C out front so that it does appear on the left side. Well, here we have C times the 0 vector since U is in null A, and of course this equals the 0 vector. So therefore, null A is a subspace of R to the n.